we have to discuss today the Laplace transform. In short, it is LT. L stand for Laplace and T stand for transform. Basically, what is going on here? We are just transforming from time domain f of t to frequency domain f of s, and from frequency domain to time domain. So this is the basic core that we have to carry out during the discussion. So we can have the definition. The Laplace transform is Laplace transform a signal from the time domain to complex frequency domain or S domain. That is f of t transferred to capital F of S, or from capital S f of S to small f t, where this S is a complex frequency expressed as sigma. S is sigma plus j omega. The sigma is real part, and this gives the how fast signal is dropping. Signal is dropping means attenuation, that is concerned with the real part, and it is the attenuation. The imaginary j omega is imaginary part, which is the oscillation frequency. This gives the oscillation frequency of the given transform. Symbolically, it is represented as L of ft. Time domain का Laplace transform है frequency domain, and it is expressed as minus infinity to plus infinity f of t e raised to the power minus st dt, a double-sided transform. Double-sided means if it is 0, so minus infinity to plus infinity. This is double-sided. And if it is 0 to infinity of ft e raised to the power minus st dt, so it is single-sided Laplace transform. So in this way, we can call the Laplace transform in both ways, single-sided and double-sided Laplace transform. Now, you have remember, in case of the Fourier transform, we have given f of s is 1 upon under root 2 pi minus infinity to plus infinity. This is f of t of minus a I a t dt. Now this one is the. So here the exponential power is e raised to the power minus I a t, something like this. That is this is imaginary part. It is imaginary part. But in case of Laplace transform, this L of ft is minus infinity to plus infinity f of t e raised to the power st, e raised to the power minus st dt, where this part, that is e raised to the power minus st. So s contains sigma plus j omega t. It means e raised to the power minus jt into e raised to the power minus j omega t. So in case of Fourier transform, we are using only e raised to the power minus j omega t. In case of Laplace transform, we use e raised to the power minus sigma t as well, in addition to that. And that's why the Laplace transform has a different feature than the Fourier transform. So this Fourier Laplace transform helps in solving the differential equation with boundary conditions without finding the general solution, without finding the general solution. And the value is, and the value is values of the arbitrary constants, value of the arbitrary constants. So this one is the important feature of this Laplace transform over the Fourier transform. So we consider both the cases. And one feature is Laplace transform is applicable where we cannot use the Fourier transform as well. In many functions where we cannot use the Fourier transform, then we use the Laplace transform. In the Laplace transform, there are certain formulae of the Laplace transform and its proof we will have to. So, formula of Laplace transform and its proof. First is the simple Laplace transform of 1 unit is 1 by s. Laplace transform of 1 is 1 by s first. So let us prove it. Consider L of t. L of t is from 0 to, you can say minus infinity, but here it is 0 to infinity, f of t e raised to the power minus st dt. So in place of ft, we have 1 into e raised to the power st dt, and that is 0 to infinity e raised to the power minus st dt. So integrate this one is e raised to the power minus st dt upon minus s. So minus 1 by s. Here it is e raised to the power minus st from 0 to infinity. 0 to infinity. So this is minus 1 by s, 1 upon e raised to the power s into infinity, this minus 1 upon e raised by s into 0. So what will get? Minus 1 by s, e raised to the power infinity is, this is infinity, 1 upon infinity, minus 1 upon, this is 1, e raised to the power 0 is 1, this minus 1 by s, 1 upon infinity is 0, this is minus 1. So minus 1 by s into minus 1, so it is 1 by s. So the LT, L of 1, L of 1 is constant, so L of 1 is 1 by s. This is the Fourier transform. The second is L of t raised to the power n is equal to factorial n upon s to the power n plus 1. So consider L of t raised to the power n is 0 to infinity t raised to the power n into e raised to the power minus st dt. So this is 0 to infinity, this is 0 to infinity, or you can consider this as You can consider this as a substitutional method, and this substitutional method is you can take e raised to the power s of t is equal to x. So t is equal to x by s, and dt is equal to dx by s. So this is t is equal to, this t is equal to s by x by s to the power n into e raised to the power, this is minus x, and here it is dx into upon s. So this is nothing but this 0 to infinity. You take this is 0 to infinity x ke power n upon s to the power n e raised to the power minus x dx upon s. So this is s raised to the power n, and here it is 1. So we'll get 1 upon s raised to the power n plus 1 outside of the bracket, and within the bracket 0 to infinity x raised to the power n e raised to the power minus n dx. So this is the standard. This is the standard integration, and this integration is nothing but factorial n. This is factorial n, and so this is s n plus 1. So this is about the proof of second formulation. The third formulation is you can have the exponential. The third is let f of Laplace transform of this one is e raised to the power at. So you have this is 0 to infinity e raised to the power at into e raised to the power minus st dt, that is 0 to infinity e raised to the power a minus s t dt, a minus s t into dt. So we can integrate this one is 0 to infinity e raised to the power minus s minus a dt. So this is e raised to the power minus s minus a divided minus s minus a from 0 to infinity, this value. Now putting the limit, we will get minus 1 by s minus a, and here 1 upon, this is 1 upon infinity minus 1 upon 1. So it is 1. So it is 1, that is minus 1 by s minus a into minus 1. So this minus minus plus, so it is 1 by s minus a. So the L of e raised to the power at is equal to 1 by s minus a. Fourth formula is the Laplace transform of L is of the sine at. So this is expressed 0 to infinity sine at e raised to the power minus st dt. This can be expanded as sine at is e raised to the power at I minus e raised to the minus I at divided by 2I into e raised to the power minus st dt. E raised to the power minus st dt. So we can segregate these components, and we find that we find that uh, the factor, it is 0 to infinity e raised to the power this iat into e raised to the minus st dt upon 2I minus 0 to infinity e raised to the power minus at into e raised to the power st 2I dt. And then we have this, after solving this one is 0 to infinity e raised to the power I a minus s t dt, 0 to infinity e raised to the power minus taken common s plus I a t dt. So as we have the value e raised to the power at, this is s minus a. If it is minus a, then this minus minus plus. So this value is 1 upon this minus I a s. Here it is minus 1 upon s I a a. So we'll get this one is this minus, that is 1 upon s minus I a minus 1 upon s plus I a. So, and this whole thing is 2I. This 2I is 1 upon 2I. This is 1 upon 2I, 1 upon 2I. So this is s square minus I square a square, and this is s plus I a minus s minus I a. Whole thing is divided by 2I s minus I a whole square. So this minus a plus cancel, minus minus plus 2I a upon 2I s square plus a square. So 2I cancel, that is uh, that is L sine at is equal to a upon s square plus a square. The fifth one is L of cos at, that is L of cos can be directly alternate method of the above also, e raised to the power I at plus e raised to the power minus I at divided by 2, or you can have 1 by 2 L of e raised to the power I at plus 1 by 2 L of e raised to the power minus I at. So this is 1 by 2 e raised to the power I at. E raised to the power I at is nothing but, it is, as we have already discussed, it is 1 upon s minus I a plus 1 by 2 1 upon s plus I a, s plus I a. So 1 by 2 here, by solving s plus I a plus s minus I a upon s square minus I square a square. So we see I a is cancelled. This I A is cancelled. S plus S divided by 2. Here it is. So it is 2S by 2S square A square. So this 2 cancel. L cos AT is equal to S upon S square plus A square. The sixth formula is the hyperbolic. L of sine hyperbolic AT is equal to L of 1 by 2 e raised to the power 80 minus e raised to minus 80. That is 1 by 2 L of e raised to the power 80 minus 1 by 2 L of e raised to the power minus 80. So this is 1 by 2. That is 1 upon S plus A minus 1 by 2 1 upon S minus A. So this S minus A, S minus, this is S minus A minus, so 2, so it is A upon S square minus A square. Seventh is similarly cos hyperbolic L of cos hyperbolic LT, that is L of 1 by 2 e raised to the power 80 plus e raised to the power minus 80. So this is 1 by 2 L of e raised to the power 80 plus 1 by 2 L of e raised to the power minus 80. So by solving, we have S upon S square minus S square, A square. This is the functions. Now the other part is the important sections of this Laplace transform is differentiation. That is differentiation with respect to time. Differentiation with respect to time. The first formula, that is L d by dt of f of t, if you are differentiating, so it is s f of s minus f of 0. The second important is L, the second order differentiation d2 upon t square of f of t, then it is s square f of s minus